Hello all, this is Y.Renuka from 4th ECE-C. My roll number is 19BQ1A04H5 and now I am going to discuss about image transforms from the subject digital image processing. First of all, let us discuss about the need for image transforms. Image processing operations can be applied both in spatial and frequency domain. Many imaging operations can be directly performed in the spatial domain by manipulating the pixel areas. The main advantage of spatial domain operations is that they can be visualized easily. However, the same operations can be done in frequency domain, which deals with the frequency components of the image. Some of the real applications of the image processing are biometric applications such as fingerprint based attendance, airplane baggage screening system, radar image monitoring. The change of domain for image processing operations will be convenient for processing, and we can also gather more details about the same object by changing the domain. Some of the practical applications of image transforms are: certain operations are easier to perform in frequency domain compared to spatial domain. For example, the convolution operation can be reduced to multiplication in the frequency domain. This leads to faster execution as well as efficient design of algorithms. Transform of useful is useful in gaining valuable insight into concepts such as sampling. The property of energy preservation states that signal energy is preserved, that is, when the transform is applied, that the energy of the signal is unchanged. The property of energy compaction states that a large fraction of average energy of the image is packed into a few components. This is uneven distribution of energy in the transformed image results in many components having negligible energy. The implication is that if a transform is applied, most of the energy is packed into a few coefficients, resulting in more zeros and small coefficients. This is used as an advantage for designing compression algorithms. Image transform helps to design faster algorithms. Spatial frequency transforms helps in asserting the image quality. The operation becomes much simpler and less time complexity. Some of the image transforms are of discrete sine transform, discrete Fourier transform, discrete cosine transform, Hadamard transform, and Walsh transforms. Now let us discuss about two of them: discrete cosine transform and Hadamard transform. Coming to discrete cosine transform, the discrete cosine transform of an 1D sequence of length n can be given as C of u is equals to W of u, sigma x is equals to 0 to n minus 1, f of x cos of pi 2x plus 1 into u by 2n for u is equals to 1 to n minus 1, where W of u is equals to 1 by root n for u equals to 0 and 2 by root n for u not equals to 0. Inverse 1D discrete cosine transform is f of x is equals to sigma u equals to 0 to n minus 1, C of u into W of u cos pi into 2x plus 1 u by 2n. And 2D discrete DCT of n by n size is C of u comma v is equals to W of u into W of v, sigma x is equals to 0 to n minus 1 and sigma y equals to 0 to n minus 1, f of x comma y cos pi into 2x plus 1 into u by 2n into cos 2y plus 1 into pi into v by n for u comma v equals to 0 to n minus 1. And inverse 2D DCT is f of x comma y is equals to sigma u equals to 0 to n minus 1, sigma v equals to 0 to n minus 1, W of v, C of u comma v cos pi into 2x plus 1 into u by 2n into cos 2y plus 1 into pi v by 2n. The discrete cosine transform is helpful in removing redundant data from an image. The DCT is separable, that is, the transformer for rows and columns are identical. G is equals to A into F into A is equals to, and the inverse is F is equals to A inverse into G into A inverse, that is equals to A transpose into G transpose into A transpose. Coming to Hadamard transform, the equations involving the Hadamard transform are: 1D forward kernel of our Hadamard transform is G of x comma u is equals to 1 by n minus 1 whole power, sigma I is equals to 0 to n minus 1 bi of x into bi of u. Expression for 1D forward Hadamard transform is h of u is equals to 1 by n, sigma x is equals to 0 to n minus 1, f of x minus 1 power sigma I equals to 0 to n minus 1 bi of x into bi of u, where capital N is equals to 2 power small. 1D inverse kernel for Hadamard transform is h of x comma u is equals to minus 1 whole power x is equals I equals to 0 to n minus 1 bi of u into bi of x. Expression for 1D inverse Hadamard transform is f of x is equals to sigma u equals to n minus 1 h of u minus 1 whole power sigma I equals to 0 to n minus 1 bi of x into bi of u. The 2D kernel are given by g of x comma y u comma v is equals to 1 by n sigma e minus 1 whole power sigma I equals to 0 to n minus 1 bi of x into bi of u plus bi of v into bi of y, and h of x comma y is equals to minus 1 into sigma I equals to 0 to 1 bi of x into bi of u plus bi of v into bi of y. And the forward transform h of u comma v is equals to 1 by n sigma x is equals to 0 to n minus 1 sigma y equals to 0 to n minus 1 f of x comma y minus 1 whole power sigma I equals to 0 to n minus 1 bi of x into bi of u plus bi of v into bi of y, and f of x comma y is equals to sigma n u equals to 0 to n minus 1 sigma v is equals to 0 to n minus 1 h of u comma v into minus 1 whole power sigma I is equals to 0 to n minus 1 bi of x into bi of u plus bi of v into bi of y. The Hadamard matrix for lowest order h of z is equals to minus 1, 1, and minus 1. The Hadamard matrix for nth order and is hn is equals to hn, 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 and minus hn. Thank you.